Hello everyone. Today's topic is the frequency domain. Now, until this point, we've used the time domain methods, where we analyze the systems in terms of their poles and zeros, where we utilize the root locus plot, um, where we had some formulas for settling time, overshoot, and rise time and peak time, etc., which then were mapped into a pole pair. These all kinds of analysis and synthesis tools were in the time domain. Now, in the frequency domain, we are actually talking about the Fourier transform, or actually we have the Laplace transform as a transfer function, but then we substitute it so that it becomes the frequency domain, so the Fourier transform, and we'll analyze the system or also maybe synthesize some controllers using the frequency domain methods. Now, the basic root of the frequency domain is, of course, the Bode diagram. Therefore, we need to know what the Bode diagram does, how it is obtained, and what characteristics it'll carry of a system. So let's actually start with the Bode plot itself. Now, here we are not going to talk about poles and zeros, nor are we going to talk about some root locus plots. The only thing that we will focus on will be the Bode plot. Now, how do we obtain a Bode plot, or what does a Bode plot tell about a system? Well, in the frequency domain, we're now interested in different frequency inputs. For example, we'll just fix it to sine omega t because all kinds of inputs can be used or can be decomposed into its sinusoidal individual frequencies, and there some will give us basically the signal that we're looking for, which is basically the Fourier transform. So we have a spectrum of signals, therefore we are looking at the frequency. We will apply some different frequency inputs, and then we'll observe basically the output here. Since this is a linear time invariant system, it doesn't actually change the form of the signal, it doesn't change the frequency, because we're not able to change the frequency unless we change the source. In signal processing or in signals and systems courses, that's already what you know from. The thing is that the frequency is dependent on the source, and if you don't change the source, the frequency will stay the same. Now, this is a linear time invariant system, which means that if we apply a sine wave with unit amplitude and some phase angle 0, the output will of course change its amplitude, so a times sine, and its phase. So the only thing that is changed here is basically the amplitude and phase. And where does this come from, or who decides on what the amplitude is going to be, what the phase angle is going to be? Well, of course, the system itself. Now, of course, I'm writing down GS here, but we should note that if you look at the Laplace transform integral and compare it to the Fourier transform integral, you'll see that there's a slight difference where we have s equals j omega. Now, we had the substitution before, but it's not the same, because before we talked about a characteristic polynomial, and if we have a certain root on the j omega axis, so s equals j omega, it should satisfy the characteristic polynomial if it's a root of it. So therefore, this is not the same substitution. It may seem the same, but it's not, because here the aim is to look for the roots of a characteristic polynomial. Here, we substitute this whole thing into the transfer function itself. So basically what we are going to do is we're going to use substitute GSS instead of s 1i times omega. So sims omega real. Therefore, this will give us a different thing. It's not going to be the same. Now, let me comment out this whole stuff here, and let's see what this will result in. Yeah. Don't know what that was about, but yeah. So let's run this. Now, as you can see, since this is basically a fraction of polynomials, and since we substitute s equals j omega, which is a complex number, and omega is the unknown, we kind of have a complex valued function that looks like this here. Now, of course, if we plug in omega, let's say omega equals 0, for example, then this will vanish, and then we will end up in 1 divided by 24. If we, for example, substitute something else, we'll see that it will be a complex number. And that's basically it. It's a complex number that depends on omega. And when we change omega, when we change the frequency, the complex number will change. Of course, this is given in Cartesian coordinates, which we can then maybe change into its phasor form, where we have then the amplitude and the phase of the complex number. So basically what we're going to do is we're going to work in polar coordinates, and that's it. We'll analyze a system in polar coordinates when we change omega. This will tell us, hopefully, much about the system. So if we do the substitution, we need a certain vector, omega vec, let's say 0.1 with 0.1 up to 0.4, for example. Now, therefore, we will have g omega here, and this will give us a magnitude, zeros size of omega vec, and of course a phase, so zeros size omega vec again. Why do we need this? Well, we can have multiple omega values. Therefore, I defined a vector, and at each frequency we will have a magnitude and a phase that will be applied to the system, so to the input basically. So the amplitude of the transfer function, or the complex number resulting from the transfer function, and the angle or phase angle of the transfer function will basically determine how the sinusoidal wave will be outputted here. So unit amplitude, g omega, will be the amplitude at that specific frequency. So we're working with a specific frequency, omega star. And again, at that frequency, we will have basically a phase angle. And that's basically it. So, yeah, let's see how this looks, because we will plot this. And the common axis is going to be omega. Therefore, let's actually open up a for loop here. Length omega vec, and omega val will be omega vec I, and then we will have a that is going to be double substitute g omega instead of omega, omega val, and then maybe the real part of it. The same goes for b, which is going to be the imaginary part, where we call the complex number a plus bi. So that's what I'm trying to accomplish here. So we know that the magnitude, the ith magnitude, will be the square root of a squared plus b squared. So that's nothing new. But then again, we will have the phase angle. Now this should be in degrees, because it makes stuff easier. So a10 to the b comma a should do the job. And then of course we need to create a figure with a subplot. Hold on, grid on. X label going to be the frequency. They will be aligned. Y label is going to be g omega. And then we'll plot omega magnitude with line width 3, ax2, the argument or the phase, therefore phase. Of course, omega is not the vector, it's omega vec. So there we go. Now, First of all, this is basically the mathematical way of obtaining the body diagram, which still doesn't look like a body diagram, but we'll get on that. But if we think about this here, it could also be generated experimentally, where we have basically a sine generator with input omega, where we change or tune omega with these values, for example, and then we observe basically the output, and in the steady state we have to measure its amplitude, note that down, and then its phase angle, and then plot that. So this is basically the experimental way of doing it. And for that we could use MATLAB and LSIM or maybe Simulink, and we could obtain the same thing. But of course we can do it numerically, mathematically, so why not do it like that? Now, the basic difference and the reason why this doesn't really look like a body diagram is, first of all, we need to change our omega vector. Since we are looking at it in different frequency regions, like low frequency, mid frequency, and high frequency regions, it is logically to have a log space vector so that we can cover both 10 to the power of -2 and 10 to the power of 2, for example. Pick like, I don't know, maybe 200 points, and then generate this plot. So let's change it again. But of course, still we're not satisfied with this, because the x-axis, which is the frequency itself, is spaced linearly on our plot. And that's not what we did. We basically chose it to be logarithmic. In order to be able to fix this, we need to basically have a little hack here, which basically takes the get current axis handle and accesses its x scaling and then converts it into log, which is linear or lin by default. So let's run this. Now it's more like a body plot, especially when you look at the magnitude plot here. The phase plot is also okay, but then there's a discontinuity, and the reason for that is basically this ATAN here. Of course we have to fix this, and the way of fixing this is basically to equate this to so we have to take the mod of phase 360 and then add, I guess, 360 or subtract it, I don't know, we'll see. Yeah, I guess we should subtract it. There we go. Now, this is a little fix that we need to apply to it so that we have a continuous phase angle, because it doesn't make sense to be to have a discontinuity here. This is because of the ATAN asymptotes, and it's on the wrong side basically, and we fix that with this line 21. Of course, this is not the way that we are going to always obtain the body plot, because it doesn't make sense. We can just directly use mag, phase, and omega with the body command that we have at hand. But then again, the magnitude here with the body command is a little bit different than we expect it to be, because it is possible to have multiple input, multiple output systems, MIMO systems, and then there would be some input channels and output channels, and between input and output there will be always a body diagram. So the body command is basically prepared to work with that. So we have this 3D structure where input channel, output channel, and then the element is going to be in this data structure. But we don't really need that when we are working with basically SISO systems, single input, single output systems. So therefore, I'm just going to use the squeeze command in order to get rid of the extra dimensions that are not necessary at all. Now at this point, when we run it, we will get magnitude, and it's a vector as we want it to be. Now we can then, of course, copy this, paste it. Let's verify if our body calculations are correct or not. Now it's going to be omega. And there we go. Now let's put them side by side. You can see maybe the frequency changes a little bit. It's 10 to the power 3 that we could fix basically, but you can see it is the same. The scaling is a little bit, is it off? No, it's actually almost the same, but the only thing, the difference is that we stop at 10 to the power of 2, whereas the body command generated up to 10 to the power of 3. So now, of course, let's get rid of the body calculations. This was just an introduction to the frequency domain and to show you how we treat transfer functions. We actually don't treat them like transfer functions. We convert them into its Fourier representation, which is basically depending on omega and is a complex number. And then we convert them to polar coordinates. Then we have magnitude and phase, and everything will be about magnitude and phase from now on. So let's get rid of this. Let's put it here, and let's get rid of this here. So omega and omega. There we go. Now this is our body diagram. Now we have a system, and it's a third order system, and we're looking for its stability interval. So what about stability? Now, since the closed loop transfer function is written down like k times gs and then divided by 1 plus k times gs, and since we're using s equals j omega substitution here, what we have to do, or what we can do, is basically we can change the subscripts to omega. And we have to remind ourselves that everything is a complex number from now on, because before that it was a rational of polynomials. Now we're looking at a complex number. So if we want to have something, if we apply a certain input, a sine wave, into its input, and we want to obtain infinity, or something that tends to infinity, here we have sine input, which is a bounded input basically. And if we want to see something tending to infinity, the only thing that we can do is basically multiply it with a division by 0. Then, and this should be basically the closed loop, then this might tend to infinity, tend to inf. If we have a division by 0, then naturally the amplitude becomes infinity, and therefore the signal should be multiplied with that, which should also tend to infinity, which we call instability. So therefore we are going to look for something that makes the denominator 0. In this case it will be 1 plus k times g omega, because our closed loop is constructed with the system and a p-type controller. Therefore this should not be equal to 0 if we want to have a stable system. And the reason is that we will have a division by 0, which will tend to infinity. So this is basically an equation, but everything is a complex number. So if I work on this, this would become equal to -1. And at that point, I can convert this into polar coordinates, which should give me a magnitude of 1 and a minus 180 degrees or 180 degrees. So now, at this point, what I have to do is, or what I can do is, I can state the following. The amplitude should be equal to 1, and the argument of k times g omega should be equal to negative 180 degrees. If we satisfy both of them at the same time, if they're simultaneously satisfied, then we will get the instability or the instability point. Now let's have an assumption that k is positive, and let's look at this. Now I can see that k is going to be a positive k outside of this modular here. And yeah, if I look at the argument, I know that the multiplication of something, the argument of that, is going to be the sum of the arguments. So plus argument of g omega. Now I know that k is a positive number. If it's negative, I'm going to place negative 180 degrees. But if it's positive, it will have argument 0. Therefore, I did get rid of that. This is going to be one equation, and I can also state that k is going to be 1 divided by the magnitude of g omega. Now this tells us something. This tells us the following. We can use the phase plot of the body plot of the system and look for a certain frequency where the argument or the phase angle is equal to minus 180 degrees. At that frequency, if we also change the gain of the controller or change the gain of the system such that the controller has the gain 1 divided by g omega, and if you multiply this with the gain of the system itself, it will satisfy basically the magnitude condition 1, then we will end up in 1 and minus 180 degrees at the same time. This will then cause a division by 0, which means infinity. The algorithm for coming up with the upper bound of a p-type controller is going to be as follows. Look at the phase plot. Determine the frequency at which it is equal to minus 180 degrees. Switch to the gain plot, look for the same frequency and read the magnitude, take the inverse, and that's your k value. And that's it. Now we have an assumption up here. Let's have another assumption which goes like this. Let's assume that k is negative at this point, because as you know from the time domain methods, we have a positive root locus and a negative root locus. Therefore, we should consider the positive gains for once and the negative gains. So now I'm doing that. Now the same applies here. We will have the sum of arguments again. But now k is negative 2. So we will have a negative 1 here that causes negative 180 degrees. Now k is negative, so it will also cause the same, which means that the argument from the system or of the system should be equal to 0. And from this part here, I can see that k is going to be extracted as minus k, because k is negative, so it should be a positive number. So negative k times this, which then can be converted into 1 divided by the gain of the system. Now we have this negative sign, let's plug it in here, and omega star. So now this is basically another point of interest that we should look at. And here we see that we have omega star. At a certain frequency, the phase angle of the system should be equal to 0. At that point, we should read basically the gain of the system, take the negative inverse, and we will have the negative bound of stability. So basically, to sum it up, we only need to check these points, and both of them rely on the fact that the multiplication of k and g omega should be 1 and negative 180 degrees. And the reason for that is division by 0. So now, let's actually calculate this. Now let me comment this out. Usually what you need to do is you need to look at it visually. You will basically have a table of values or a body plot itself where you are going to search for certain values. Now I am using MATLAB, therefore what I can do is, since I have the vector of elements, I have the magnitude vector, I have the phase vector, I have the frequency vector at same size. What I can do is I can search it basically programmatically. How am I going to do that? Well, the only thing that I should remind you of is that we shouldn't search for exact values because they might not be available. If you look at the omega vector or maybe the magnitude vector, you can see that these values are interesting, but for something like the phase value here, you can see the values are quite distant from each other. We can fix this, but you might not hit the target when you're looking for minus 180 degrees. As you can see here, there is no exact value of minus 180 degrees. So what I'm going to do is I'm going to look for the closest one, and that should be enough for me. So therefore, I'm going to construct something that looks like this, an error signal basically. And I'm going to look for basically the phase plot minus 180 degrees. And I'm going to take the absolute value of this. So abs of this. Now, I don't really need to use a for loop. If you wish, you can. Of course, you can go ahead and do that. But since MATLAB can work with vectors and elements quite easily and flexible, I'm just going to use some MATLAB magic here. You can see that I give it a vector and then a value, and take the difference, take the absolute value, and everything will work. Therefore, we will have something like the following. And as you can see, there's a high error, and then at some point it tends to be 0, and then it increases again, because this is basically the vicinity of the solution that we're looking at. And I'm just going to take basically the value and index using the minimum here. We've used this before in tabulation, where you can look for the best solution or the optimal solution. It will give you the index and the value. Here the value doesn't really mean that much, so I'm just going to go with the index. So omega index, and then magnitude index, and then phase index are going to be the values that I can read from the body plot here. So there we go. We have something here, something here. So this is the frequency, this is the magnitude, and this is the phase angle. So let us actually define them as omega val, and then mag val, and then phase val. Let's display them basically. So that's going to be string omega val, and then magnitude, phase. There we go. Now we know how to also calculate the controller or the gain, the corresponding gain. So 1 divided by mag val. So let's also maybe show that. K is going to be K. Now, according to this, at frequency 6.21, the magnitude is 0.00250, and then the phase angle is minus 184, and the gain is 401. Of course, this is not quite correct because the phase angle is a little bit off. What we can do is we can provide our own frequency vector here. So between -2 and 2, maybe let's pick more points, like 500 points. If we run it again, we will see that the accuracy is way better now. So we approached it at 179.9689, which is quite good in my opinion. And the gain is 349.64. So there's a big difference. The frequency did also change a little bit. And the reason for that is the amount of points need to be increased in order to increase the accuracy here. So we can also repeat this thing for the negative one. So let's do that. Instead of searching for minus 180 degrees, we're searching for 0. And the only thing that will change is the sign of K. And yeah, that's basically it. Let's run it again. And as you can see, we hit the target at 0.01 frequency. And then the magnitude is this here. And the phase angle is not quite 0, but almost 0. And therefore we get -24. Now the stability interval of this system is therefore between -24 and 349. Now, what we can of course do in order to validate this is just plot some root locus here. Let's actually do it like using a subplot. And then the negative root locus on the second plot. We're interested in the poles, so um, 350. Let's take 350 times gs, 1. Real c-poles, imaginary c-poles, and then negative 24 should be basically the next one here. So there we can see that basically we have them here. Let me just quickly do something here. Let me quickly find that. There we go. Let's actually apply this. Yeah, there we go. I'm sorry. Now we can see actually that at this exact point we have our values, and interestingly enough, there's also some other similarity here where you can see that the frequency or the point where omega on the j omega axis is basically the same value here. So even if we talk about the fact that if we plug in something into the characteristic polynomial and if we're using the Bode method, they're not quite the same, but of course the frequency or the crossing where it happens is going to be the same. So it's of course we have numerical differences, but theoretically they're equal to each other. So if you see a certain frequency here, you can assume that the crossing is also at that point. So in the closed loop, it should be J 5.8282 and its conjugate, and we have that here. And the same goes for here. You can see it's almost 0 because it's a origin crossing on the negative root locus, and that should be 0 basically. So the Bode plot also tells us the frequency of crossing, and therefore it's always important to remember that the j omega axis is basically the Fourier domain, whereas the whole S domain is the Laplace domain. So we have a little projection on j omega, and it quite makes sense to be able to analyze the system in terms of stability if we use j omega. So we can see that the data that we've obtained from the Bode plot is basically aligned with our results. So what we still can do in order to help you visually is we can basically define this ax1 and ax2, and we can also plot the interest of point. Let's have plot omega val, mag val, and then maybe kx, and then line with 3. This should go on axis 1, and AX2 should be phase well. Let's repeat it here. Let's run it again. Now you can see we've chosen this point here and also this point here. Now, if you have a body plot, what you're looking for is you're looking for negative 180 degrees, which is somewhere here. You draw the line, find out the frequency, you draw the line, and then you have the magnitude. Take the inverse, and that's your upper bound. Look for phase 0, which is approximately here, and at that frequency, the gain is this one here. Take the inverse, put a negative sign, and you have the lower bound. So therefore, we can see that the system will be stable between -24 and 350 approximately. So this is how we approach a system in terms of stability. But let me also remind you that the system has an overall gain here. And when the gain drops, we have something called the corner frequency somewhere here, which is going to be square root 2 divided by 2 times the original gain here. We call that the corner frequency. We can use this for bandwidth calculation and stuff, but we can see that the amplification tells us also a story about the system. If we have high frequencies, if it's higher than 10, it will basically get rid of the signal. It will reject the signal because it will be amplified with almost 0. So there will be no output whatsoever if you have the system as a closed loop. But the system does also not very well if you have low frequency type inputs because the gain is 0.04. So the system attenuates the system, or maybe also rejects all the inputs, because technically 0.04 is something of a magnitude of a noise. So we cannot really distinguish if it's noise or if it's going to be the actual signal. So this is a very bad scale system. We need a certain gain in order to tune the system to be able to, for example, track some references. Ideally, what we want to have here is that this line should be at equals 1, so gain 1, so that we are basically outputting our input. And then at some high frequencies, we should have 0 to reject basically high frequency signals, which is probably noise. Because references, they will not have high frequency components whatsoever. Of course, they will have maybe some of them, but the whole signal will not be a high frequency signal. Therefore, we want to have low frequency tracking, high frequency rejection, since we know that noise is high frequency. Of course, disturbance is also low frequency, so that causes a bit of an issue because we have disturbance and the reference signal in the same basically frequency range. But yeah, we have to look at the transfer functions and come up with a design for that. Now, this is basically how we treat stability. And as you can see, the algorithm in the finding out what the frequency is basically standard. And we will always look for the phase angle -180 degrees and 0 to conclude the stability bounds on the positive and negative root locus respectively. So let's move on. We have checked the stability of a system. What about designing a p-type controller for 10% overshoot? Now, when we're going to design a controller, first of all, we see that we have 10% overshoot. Therefore, we need to calculate our zeta, no matter what, divided by the square root of pi squared plus log overshoot squared. Now we have zeta here. But then again, we need something called phi m, which I'm going to explain in a moment. I'm going to use a10d, and it's going to be 2 times zeta divided by the square root of -2 times zeta squared plus square root of 1 plus 4 times zeta to the power of 4. Now, our way of designing a controller will basically go as follows. We know that if we have -180 degrees as a phase angle, we know that this point corresponds to marginal stability. We are on the j omega axis. And if we apply a certain input at this frequency, we will get a sine wave. And if we would apply a step type input, we still would get a sine wave. So this would correspond to 100% overshoot, because 101, 101, and you're increasing basically, and it will get out of control, so it's not going to be stable. We know for a fact that if we are at the j omega axis, even if we apply a step type input, the output will be a sine wave, and that will correspond to 100% overshoot. And we also know that if we go back a little, that we will basically decrease the gain of the system, of the controller, and this decrement here will correspond to a certain low zeta value. So we will be a little bit off, or we will have a slight angle with the j omega axis, which will correspond to a slight zeta value. Not zero, but a little bit more than zero. And we will not have 100% overshoot, we will have lower overshoot. Let's assume 95%. If we move a little bit more, it will decrease k a little bit more, and then the zeta value will be increased a little bit more. Therefore, our overshoot will drop a little bit. At a certain point, for example, at this point exactly, or maybe this point here, at this point, we will have zero overshoot, because all of them will be on the real axis for this system specifically. That tells us that we will have a certain point where we will have zero overshoot. We know the point of 100% overshoot. So we need to come up with a way of kind of ratioing it so that we can say, okay, this point here should be basically the overshoot that I want. And at this point, it's about the distance from the marginal stability point, which is called the phi m, the phase margin, because it's a margin on the phase plot, and it is a distance between our point of interest and the marginal stability point, minus 180 degrees. So this formula will help us in determining basically how much distance we should go on the phase plot so that we get the overshoot that we're looking for. There's an alternative formula, or alternative way of doing this, which is 100 times zeta, which is way more simpler than the one here, but you can use both of them. Now we know that zeta is 0.59 for 10% overshoot, so 100 times that will give us 59 degrees. So what this means is that we will need a distance of 59 degrees. So since we are looking at minus 180 degrees, if we add them together, we will get something like the following. Let's see what it is. 100 minus 121. So we're claiming that if we design a controller that will end up in this phase angle instead of minus 180 degrees, we should get the overshoot value that we're looking for. So let's test that. So how can we basically test this? I'm just going to take this one here, and that's it. If you're using MATLAB, it's quite simple to design a controller for the p-type controller, or maybe obtain the stability interval, because you will always use the same piece of code with slight differences, with slight updates. So I'm not going to look at this, I'm going to look at plus phi m. And that's basically it. 10% overshoot, calculate zeta, use zeta to come up with phi m, whether it is 100 times zeta or the ATAN formula. And then I'm looking for the closest point on the phase plot, get the index, read the frequency, read the magnitude, read the phase value, read a base, or use the magnitude value in order to come up with the controller, and that's basically it. What we could do is we could also maybe well, we don't need anything else. Let's actually just plot something in red, and that's basically it. So let's run it and see what we have here. So you can see it is approximately 121.43, and the gain value that we should use is 80, and the frequency is 2.44. Now, I would like to do something like this, since I know what the gain is going to be, I can just connect them and use step info on this, and maybe also plot the step response. There we go. Now, of course, we need the step response. We should also grid on maybe. And that's it. Now, since we know this here, what we can do is we can display basically the overshoot value, info.overshoot, maybe also setting time, etc., but that's not really needed, so let's skip that. Now we can see that the overshoot value is not quite correct. It is 26%. What is the reason behind that? Well, this was an approximation, and as you might guess, we still have zeta in our formula. That would mean that we are talking about a pole pair, but we have a third order system here. Therefore, we have 3 poles, and the overshoot to zeta to phi m mapping might not be quite correct because it's about a second order system. Here again, we see that the second order system is quite important, and most of the formulas are again obtained for second order systems. But it doesn't mean that you cannot use it for a third order system, but you should be aware of the fact that that might give some incorrect results because it's not meant for third order systems. What we can still do here, and this is a more practical view. Now, if you are not asked for it, if the question doesn't tell you to tune it, you should maybe leave it at this point and then make your point that this is a third order system and this is an approximation, etc., etc. But if you want to be, if you want to tune this, if you want to come up with exactly 10%, you can basically do that by maybe increasing, in this case increasing because we have to go a little bit further to decrease this overshoot value. You might want to increase the phi m value here. So let's actually add a certain amount here. Let's say 20 degrees. What happens if I add 20 degrees? It improves 10%, so maybe 20 more, and we should be good to go. As you can see, now the overshoot is 10%, and we get exactly that what we want. So it is possible to tune stuff here by increasing or decreasing it a little bit. But other than that, if you're not asked to do it, don't do it. But if the question insists on having exact values, then you might want to tune it a little bit. Now, of course, you could also say, well, yeah, I have a p-type controller. I can just try the gains, and that's basically it. But you can see that this is not quite the same here because we're using basically the body plot here. And it doesn't really matter what the system is. You can just use this body plot of that system. And we don't look at the transfer function, the model at all. We just look at the body plot. We have something in mind, namely the phase margin. If we tune it a little bit, we basically get the result that we want. Now, of course, for K, you can use K, but for all body methods almost, you can say that it is possible to tune it by just tuning the parameters at hand. So yeah. If we want to design a different p-type controller with a different overshoot value, all we have to do is we have to come up with the phase margin that corresponds to the requirement. And that is going to be basically it. Now let's go a little bit further. Let's try to add a phase lag controller. And what we want to do is we want to use this design, but we want to improve the steady state so that the steady state error will be reduced tenfold. Now, this can be done with a p-type controller. So basically what we're trying to do here is we're trying to come up with a better gain. And we know that increasing the gain of a p-type controller most of the time decreases the steady state error. So let's actually first come up with an appropriate gain that will accomplish this tenfold reduction. For that, what we need to calculate is basically we need to look at the steady state value of y. And I know that the steady state error value will be 1 minus YSS. So let's display them. YSS, string YSS, and then the same for ESS. Now what we want to do is we want to have ESS2, which is ESS divided by 10. So we will reduce that by tenfold. So this would then mean that YSS2 should be this. So let's basically display them too. There we go. Now we can see the steady state error was 0.36. If we want to reduce it, it should be 0.036. Therefore, our steady state value for the system should be at 0.96369. So how can we obtain that? Well, we know that the system is has a gain of 1 divided by 24. And I'm using basically the final value theorem here, where I plug in s equals 0. All these terms will vanish, and it will be 1 divided by 24. So if I'm using a p-type controller, it should be k divided by 24. And if I take the closed loop with this, plus 1, if I multiply everything with 24, it's going to be this here. So this is basically, I can use this equals YSS2 in order to come up with the appropriate gain value that will correspond to the tenfold reduction. So I'm going to define k here. This is going to be my problem. I'm a little bit lazy at this moment, so I'm just going to use solve the problem. And let's see if it does actually. It seems like it does, so let's convert this into double. And this should be, I don't know, ksol or something like that. Let's display this as k star, the new value, ksol. There we go. Now, 636 seems to be the one. Oh, of course. Now, let me actually change this back to its original state, where we have a little bit error, where it is a little bit off. And don't add this. There we go. Now we have 99722. So it was a higher value that I remembered. So yeah, it seems like we need this value here. So in this case, if we are using our p-type control that we've designed here, which is of gain 80, it seems like we have 0.76, which corresponds to 0.23 here. And if we want to reduce it by tenfold, we get this value, which gives us 0.97. So it's a dramatic change, by the way, because we're way off of this value, but the lag controller or another p-type controller should force the system to change so that it will basically its steady state value should be 0.9765. Now you can see that the issue here is that we are basically out of the stability region. I might want to use this value here, but it's not possible because the stability bound is 350. And of course, I will not have 10% or 26% overshoot here. The requirement is given as follows. It should be a phase lag controller that shouldn't change basically the design that much. So we are still aiming for 10% overshoot. And it should also reduce the steady state error by tenfold. So it has more than one job. And just by tuning the parameter up to 997, it doesn't cut it because it's not stable. It's not going to be stable. So the phase lag portion will be added so that it will increase the stability overall, and it will make this happen. So now what we have to do is we have to basically where is it? It's way up here. So what we have to do is we have to update our body plot for starters, and the reason for that is going to be select controller. Actually, this starts up here. So there we go. Now the reason for that is the following. We have a k star or k sol. We will have tau s plus 1 divided by alpha times tau s plus 1, and then the system. Now we know that this should be a certain gain, 997, and we know that this is a certain system, but we are going to design a lag controller. Now what I need to do is I need to get this here and treat this as the new body plot. There are two ways of doing this. I'm showing you the easier one, where I'm just going to take k sol times cs, and I'm just going to use this to plot the body plot, to update the body plot, and that's going to be it. But another way of doing this is just using the same old body plot, but then if we are reading a certain magnitude value, multiplying it with k sol. That's another way. And in some classical exams, the questions or the exam might ask you to do that. So instead of giving you 3 or 4 body plots, it will provide you the most basic body plot, and then you have to basically update the values if you have, for example, a certain case like this. If you want to see the body plot of this, the phase angle will not change, but the magnitude plot will be shifted upwards with the factor k sol. So that you should basically do your calculations manually then. But I'm not going to do that because I'm introducing you to the design methods and I'm exemplifying them, so it should be a bit easier to understand. So I'm just going to skip that, and we are going to design the controller, the lag controller now. So again, we are going to look for the phase here. So I'm just going to use the same old stuff that is given here. Let's take this up to this point. So, but there is a slight problem now, because now we have this times gs, and this should not be equal to -1 and 180 degrees, or in our case, since we're looking for a certain overshoot, minus 180 degrees plus phi m. So I'm looking at this. Now if I plug in j omega, we will have j omega here and also here. And the issue is that I'm not going to get rid of the controller part that easily, where it was the case of the p-type controller. Because the argument of this has a certain argument plus the argument of j omega, and this will have gain 1. At least gain is quite good, so that's not -1, this one. the gain is not going to be affected, so I can use basically the gain of g omega here. But you can see that the calculation of this involves unknowns. We have alpha, we have tau, which are the controller parameters, and we don't know what the values should be. So instead of doing this, since we know that we are going to aim for the same phase angle, we will assume that the phase lag controller does not contribute more than 10 degrees. So instead of arc this, so argument of this plus argument of g omega is basically the right hand side here. And if it's not greater than minus 10 degrees, I'm just plugging in minus 10 degrees, and therefore it will become argument g omega is plus 10. So I'm going to search for this point. Since the lag controller has a negative angle contribution, I don't want to mess up the stability of the system. It might be the case that I design it so that we are exactly at minus 179, and then the lag controller comes into play and it becomes 189. So I lost stability. This is something that I don't really want. Therefore, I'm going to be assuming that the angle contribution is not greater than 10 in magnitude. So negative 10, so we are going to be a little bit more on the safe side and add 10 degrees to our desired point. And we've seen that we can easily do that because that's not 10%, it's 26% overshoot no matter what. So yeah, we can just use this. Therefore, I'm just going to get rid of this. I'm going to add 10 degrees to it. Search the point, get the values. Now instead of this, we will have basically tau, which is 10 divided by omega val. And then we will have alpha, which is basically mag val itself. So now at this time instance, we've basically calculated everything that is necessary. So I'm just going to show tau and alpha. It's going to be tau and alpha. There we go. So what is the lag controller now? Keep in mind that K-sol should be included into the controller now, times TF tau 1 alpha times tau 1. This is basically it. Now, as it was the case for the p-type controller, no matter if it's the stability or if it's a synthesis problem, the steps are quite clear. And you have to just obey the rules, just follow the steps, and you are going to design a controller. That's a nice thing about the frequency domain methods, because they will be a step-by-step design method, kind of an algorithm, and you should follow the algorithm, and that's basically it. All that we did here is we added 10 degrees, but we know that the lag controller doesn't contribute more than 10 degrees. And we know that for a fact because in the time domain approaches, if you design a lag controller, you place them around the origin. And if you have a design point on the root locus, if you draw the vectors, you will see there will be a slight difference between the zero angle and the pole angle of a lag controller if it's around the origin. And it should be placed around the origin with a certain ratio, so that the ratio is, for example, 997 degrees. I mean 997. So we should place z divided by p, so that k-sol is going to be the ratio of that. But here we have a different approach. Here we don't want to mess up the phase angle, but we know that since it's a lag controller, it has low angle contribution, like 10, and we use the same value here for omega t, and we have basically the alpha value as the magnitude value at that frequency, and that's going to be the controller, lag controller itself. So of course what we need to do now is we are going to take this and instead of having a p-type controller, we have a lag controller that has the p-type controller in it, and we look for that. We display the overshoot. We calculate this. We're just going to get rid of that. And let's have another color. And let's see if it works or not. Yeah, you can see that the updated body plot is given here. The gain is way up here. And we can see that the step response is a bit different than what we expected. It is like 25 seconds, so let's maybe update the plot up to 25 seconds here. And then here also. So let's run it again. There we go. Now we see that in terms of the transients up to 5 seconds, it seems like it is the same in terms of shape, but we can see that there's a slow mode, and that's probably the lag controller here. It takes slowly action, and it forces the system to reduce its steady state error tenfold. Now we can see, of course, the specification here is not quite good because, well, it's giving up from its shape, and 97.4, as you can see here, which is this value here, it is approaching 0.977, but it doesn't look that natural here, and this sometimes happens when we are designing a lag controller. You might want to ask yourself what would have happened if we have opened up this 40 degrees. Let's see. You can see it doesn't cut it. It does the same. You could not conclude that this is basically 10% overshoot because the faster dynamics are done somewhere here, and then the lag controller slowly forces the system to reduce its steady state error. So it's not quite a good design. And you can see it says overshoot is 0, which is practically by measuring correct, but in terms of shape, it's something different in terms of expectation. If you want to have 10% overshoot, you would like to have something like this. So this behavior, but it should be amplified so that it has the steady state error that is requested here. So let us go back to the original, and this is the best that we can do with this system. We are maybe forcing it too much in this case because, well, it's just the peak value is almost there, so maybe reducing down this expectation would be a better choice. But this is just for an example, and we've seen that the K value on its own, if you look at the lag controller, you can see that the gain value here, F lag, is quite high, 67. Of course, there's also this ratio here, which is tenfold. So you can see that we have basically, so almost tenfold, I guess. We have basically a high gain value, which is K-sol, and this is basically almost 1000, and this is out of the stability region, but the lag controller compensated for that, increased the stability of the system so that we are kind of using this gain here, but you can see it is not the best lag controller design that we would hope for, but it does its job. So yeah, let's move on. Let's look at the system that has a certain delay in it. So I'm just going to open up a new file for this one. And a IO delay of 2 seconds, if I'm not mistaken. Yeah. Now, calculate the stability interval of a delayed system using the body plot. Now, it is important to analyze the system here. So before we do anything to it, let me assume that it is basically GS times minus 2 times S. And let's assume that we have K times G omega. Now, as we've stated before, this should be equal to -1 in terms of marginal stability. I'm going to plug in j omega here, and then I'm also going to plug in j omega here. So this is g omega, k, and this is basically it. Now, if we decompose it into the gain and phase, so let's have gain here, and that should be equal to 1. And let's assume k is positive for simplicity. We can see we can plug this out, so it will be k times this. And we can see that the gain of this, since this is already in polar form or in phasor form, we can see that the gain of this is basically just 1. So it doesn't change, so I'm just going to get rid of it, and k is going to be 1 divided by g omega's magnitude. So nothing different there. But if we look at the argument, so argument this should be negative 180 degrees, then since k is positive, we can maybe get rid of k directly, and we know for a fact that argument g omega plus argument of the exponent term here. Now, since this is already in phasor form, again, we will have minus 2 omega here, minus 2 omega. But then there's the problem of units, because this is in degrees, but this is in radians per second. So we have to change the units of this. So this should be times 180 divided by pi, or 314. So let me just basically calculate this. And it is going to be 57 something. Let's have 2 times included 2. So let's say 114 approximately. Now we have basically matched the units here. It is interesting because we can see that the phase condition kind of depends on omega. And we are plugging 10 to the power of 3 into omega like infinity, and this will become minus infinity. So the phase plot will be changed drastically in this case, because omega is in the equation, and if omega increases, this whole thing will decrease and it will tend to minus infinity. So a system with delay has a way more different phase plot than usual. So that's something to note. And it can also be stated that if we, for example, add less delay to it, then there will, because this is directly 2 times omega, so tau omega, so here we have tau. The less we add the delay to the system, the less we restrict the system in terms of stability. So more delay means more destabilization of the system. So adding delay to a system is not a good thing. It will give up from its stability. So what I mean by that is, well, we call basically everything that is related to this here in phasor form, minus 180 degrees. We call them the stability measures. One of them is the gain margin, where when we basically fix the gain value here, if k times g omega is equal to 1, if this is equal to 1, then we measure the distance between minus 180 degrees, and that will give us the phase margin here, which we've used to basically assign an overshoot to our design. Or when we fix basically the angle condition, the argument to if we fix the argument to minus 180 degrees, the amount of gain that can be added to the system is called the gain margin. So these are stability measures, because if you are more distant from the marginal stability point, then you will feel more safe because you have that distance between you. So, and if you're adding delay to it, you're basically getting closer to the marginal stability point. And when you're adding a delay to the system, it depends on omega. So you will eventually meet that point, or you will hit that point and you will surpass it, because omega is in the equation here, in the argument, and omega will tend to infinity. So yeah, it's quite dangerous to add delay to the system in terms of stability. Gain margin is basically how large the interval is when you're getting the stability interval. The larger it is, the better it is, basically, because you can add more and more gain to the system, and it doesn't mess up the stability. So it's a good thing to have high gain margin or high phase margin. Yeah, and you can see that the adding delay is a negative impact on stability. That's basically it. Now, when we plot this, we can just directly use the body plot here. And I'm also going to get this up to this point here, maybe, because it doesn't really matter if we have a system with delay, without delay. We will just use body, and we can calculate the body plot. We know for a fact that the gain plot will not be different than this portion here. If we have delay or not, it doesn't change, but the phase plot will change drastically, and we'll see that in a minute. Now, I'm again going to look for minus 180 degrees. I'm going to search for that point at that frequency, that magnitude, at that phase point. I'm just going to take the inverse of that. That will be my upper bound. Let's run this. And you can see, by the way, that the point of interest is somewhere here, whereas the plot goes down to a very large number. So if we want to fix that, what we can do is we can change this to be a lower value so that we zoom in a little bit more, basically. One, two. There we go. You can see we've zoomed in quite good, I'd say. Maybe a little bit more. Yeah, that's way better. You can see at something like 0.2, it's 1.58, a little bit less than that. We have already the point of interest here. And we can see that the gain value is 2.15. So let us basically copy the second part here. There we go. Yeah, that should be it. And we can see now the stability interval is between -2 and 215, and that's probably way more less than the original system, which wouldn't have 2 seconds of delay here. So yeah, the stability interval shrinks if you add more and more delay to it. And if you want to design a p-type controller, if you want to design a lag controller, I didn't mention the lead controller, but you should have them in your notes. If you want to design these types of controllers, it doesn't really matter what your system is. You will just use the same body plots and all the same rules that are given in the design steps. So it doesn't really matter if I'm looking at this system or this system. I'm just going to use the same steps. And you can see that from here, where I've just copied and pasted it basically to use it with this system. So there's no doubt that the steps are going to change, because they are not. They are just steps to carry out, and that's basically it. Now, there might be some challenges. Here, it is again possible to not give the delayed body plot here, and then you might be asked to compensate for that yourself. So you might want to use the equation that I've stated before, where I looked at the argument and also looked at the units, and I came up with 114, I guess. So something like argument g omega minus 114 times omega is going to be the angle of the system with delay. So you might want, sometimes you're going to be given a body values table, you might want to add another column, the system width delay, and then you might want to look for the omega value at that row, and then the argument of the system, and do this little calculation to update your body plot for different scenarios. What I mean by that is, if you have this taken out, and if you don't have this for a moment, you will see it will be a totally different story. And you should maybe update this here. 3. You can see it doesn't really even hit 180 degrees, and you get basically the insane values that you have here. But once you add delay to it, then you have to take into account this equation here. So this equation will then be important, because what you're going to do is you're going to look at the phase values and omega values. So you will have something like phase, omega, a table like this, and then you should basically use your equation. This equation here, you have the argument and you have omega, so you have to combine them in order to get the phase vector of the system width delay, basically. Or as it was the case in somewhere here, where we included the gain to the body plot, so we redraw the body plot of the updated system. That might not be possible. Then you have to basically look for k-sol times gs in the magnitude plot. So if you update a column or add another column to your table, you will be able to just use the updated body plot. So sometimes the classical exams will force you to do such adaptations, because you will have a basic raw body plot table of, like, I don't know, 40 or 50 different values that are necessary for you, and then that's going to be it. You have to calculate the effect of delay yourself, or if you have to add a certain gain to the body plot, you will do that on your own. Sometimes this is something that is going to happen in classical exams. It might not also happen, I don't know, but I'm just here to warn you. So there are many more controller design algorithms, but all that is needed will be in your lecture notes, because here what I'm trying to give you is basically the mentality of the frequency domain. Other than that, most of the design methods are step-by-step guidance, so you can just take the route. I would recommend you to, of course, do the homework, because there were some questions about this, but I would recommend you to solve a certain question, like if it's a stability interval analysis, if it's a controller synthesis. You will have now two different methods. One of them is going to be the time domain approach, and I would like you to just repeat it in the frequency domain. Since you know what's going on the time domain, you might want to also check it out in the frequency domain, and how the solution methods are attacking the same problem from different angles. So yeah, it is quite important to verify yourself, because we don't have that much questions with their solutions provided to you. A good way of overcoming that problem is to solve it with two different maybe methods, and it would be a good practice for exams and overall to learn the frequency domain. Now in the upcoming video, or a lecture, which is going to be the state space methods, is going to be the last one in our laboratory sessions for this semester, and see you in that session.